Hey everyone, it's Miss Lloyd, and we are looking at zeros of polynomial functions today. So the fundamental theorem of algebra basically says that whenever we have some polynomial, the highest degree that it has is going to tell you the number of zeros, whether complex or real, imaginary, any of those. So it's going to tell you how many you have. So if we have our highest exponent is the sixth power, that means we're going to have 6 zeros, whether they're real, rational, imaginary, irrational, we're going to have 6 of them. Same thing when it comes to the factors. If we have however many, whatever our highest exponent is, again, is going to be how many factors we have for that polynomial. We could have a constant on the outside, that's what that a sub n stands for, but ultimately we're going to have that many linear factors, so where we have an x to the first power. So for this first example, they just wanted to have us describe the number of zeros. So again, whenever I'm looking at the number of zeros, I'm looking at the highest exponent. I only have one variable, which is really nice, so I only have the 4 to look at. So because my highest exponent is 4, that means I'm going to have exactly 4 zeros. And that's it. We described the number of zeros, we're ready to move on. So the rational zero test. So sometimes whenever we're giving a polynomial, we may not know any of the zeros or any of the solutions that are possible for it. So in order to find at least a starting point on, okay, what could I at least test to see if this is or is not a zero, we can use this rational zero test. So we're taking the factors of the constant term, so over here at the end, whatever doesn't have a variable, so we're listing out all of those factors and we're putting them over the factors of the leading coefficient. So whatever's in the very front in front of our highest exponent. And those are going to be all of the things that we could test either using synthetic division, or we can substitute it into the function itself to see if it simplifies down to 0. So that was one of our synthetic division rules. It was our remainder theorem. So if our remainder was 0, then we knew that whatever we plugged in is a factor. And so if we plug it into the equation itself, that remainder is going to be the same as if we plugged that number into the original equation, all of the x's, and simplified it down to 0. So sometimes that's going to be an easier method than using synthetic division every single time. Sometimes you write out so much synthetic division, it takes up a lot of your paper, and then a lot of times none of the zeros actually work, or at least none of the rational ones, which means all of your zeros would be either irrational or imaginary. So sometimes if you're going to go through all that work, you might as well go through something that's not going to take up so many pages. So conjugate pairs, when we have something that's imaginary, in order to get an imaginary, we would have had to have taken a square root. In order to undo a square, anytime we take a square root, we always have a plus minus. So if I have one imaginary, I'm also going to have its conjugate. If one's a 0, the other one has to be a 0 because of that plus minus when we take a square root. And then when we're just straight up solving these polynomials, if they don't give us anything to begin with, they just give us something that's impossible to factor and they tell us to solve, one of the first things we'll need to do is find all the possible zeros, all the possible rational zeros, using that p over q. We're then going to test and see which of those actually work. We'll use synthetic division to break down our polynomial with the zeros that work, and we'll keep repeating that until we get something in the end that we could actually factor, or maybe use the quadratic formula in order to finish off. So for this first one, I'm going to it says find if possible the rational zeros of the following functions. So first thing I'm going to do is list off all the possibilities. So that p over q, I'm going to explain a little bit more about how that works. So again, my p is going to be my constant term, so I'm looking at 3. My factors of 3, the only thing that multiplies to give me 3 is 1 and 3, and it could be positive or negative. So positive 1 and negative 3 would give me negative 3, negative 1 and positive 3 would give me negative 3 as well. And then I'm going to put this over my q, which is going to be my leading coefficient. In this case is 2. So then my factors of 2 are 1 and 2. Again, I'm going to use plus and minus because positive 1 and positive 2 would multiply to give me positive 2. Negative 1 times negative 2 would multiply to give me positive 2 as well. And then I'm going to just keep all of these, or like do all the fractions. So 1 over the 1 is going to just give me plus minus 1. 1 over 2 is going to give me plus minus a half. And 3 over 1 is going to give me plus or minus 3, and then 3 over 2 is going to give me plus minus 3 halves. So I'm going to try to test all of these situations. Again, there are multiple ways to do it, and I'm going to do it very quickly. I'm going to use synthetic division at first and kind of show how it can be a little bit ridiculous. And then in the next bit, I'm going to show using the remainder theorem, so plugging everything in instead of using synthetic division. So for this first one, I'm going to try positive 1. And again, in order for this to work, that means my remainder has to be 0. So I'm looking for my remainder to be 0 whenever I'm using the synthetic division in order for this to actually work. So this first one doesn't work. Whenever I do the synthetic division, the negative 3 plus the 1 would end up giving me negative 2, and I know that that's not 0, so I'm not even going to finish that. It's not worth my time if I know it's not going to work. So now I'm going to try negative 1. And I'm going to keep doing this for all of them until I find one that works or until I work through all of them and none of them end up working. That is a possibility. It really sucks when that happens, but it is something that could occur. This one doesn't work either, so I'm going to shrink it, move it off to the side, and then try some others. So I've gone through every single one of my possibilities and absolutely none of them worked, which means that I have no rational zeros for this function, which is unfortunate because I went through every single one and that was a lot of work. So that doesn't mean that there aren't any zeros at all. It just means that they're not rational. They could be irrational, so they have a square root that sticks around, or it could mean that they're imaginary numbers. So again, like it doesn't mean that it doesn't have any. There's still supposed to be 3 roots or 3 solutions, and just none of them are rational. None of them are nice, pretty numbers that are either a fraction or a whole number, since these were all the possibilities for those, and none of them worked. So now we'll go on to the next one. So again, I'm going to do my P and Q. So my P, I'm looking at everything that multiplies to give me negative 125. So I know 1 and 125 work. There's also 5 and 25. I'm going to put all of that over. I really, really love it when my leading coefficient is 1 because that means that everything is just over plus minus 1. So it's all just my P's. So whenever I'm doing my testing, I could do the synthetic division, or I can just plug in my number to everything. So say I wanted to test 1, positive 1. I'm going to show you both ways. So I could plug it in using synthetic division and look to see if my remainder is 0. And so I end up with negative 64 as my remainder. So I know that that's not going to work. But if I were to plug it into the equation, so f of positive 1, so everywhere I have an x in my function, I'm plugging in a positive 1, so into that original function. This ends up actually simplifying to negative 64, so what my remainder was. I'm part of the remainder theorem. So again, I know this doesn't work, but this was a lot faster, especially if I plug it into my calculator, it's a lot faster than doing the synthetic division. So if I have my calculator, I'm going to be doing this to check all these numbers because it's going to be a lot faster than if I were to do the synthetic division like I did in that last problem. So I know 1 doesn't work, so I'll try negative 1. When I plug -1 into all the x's, it ends up simplifying to -216, which that doesn't work either. So then I'll try +5. And when I plug in +5, I do end up getting 0. So everything simplifies to 0. That means this works. So then I can stop my search, and I'm going to use synthetic division with 5 in order to break down this polynomial a little bit more, maybe into something that I could actually factor. And then I can find all of my possible rational zeros. And so again, I shouldn't be surprised that I got my remainder of 0 because that's what plugging it into the function told me I should get. And now I have what's remaining, an x squared minus 10x plus 25. So remember, as we divide out that what would be essentially an x minus 5 factor using that synthetic division, I'm taking everything down a notch. So where I started with x cubed, I now have an x squared. And from here, if I set this equal to 0, this is something I can easily factor using my M&A. If I'm multiplying to get 25 and adding to get -10, I know the numbers that do that are going to be -5 and -5. So my factors are very nicely x minus 5 and x minus 5. When I set each of these equal to 0, that means I'm going to end up getting +5 for both of these solutions. And since I had a +5 that worked in my synthetic division, that means I have 3 solutions that are all +5. So this will be a triple root. And all those 5s are rational. So I found all my possible rational zeros. I had a highest exponent of 3. I technically had 3 solutions, and we're on to the next. So next bit, we want to find a 4th degree polynomial function. So this means that we're going to end up with our highest exponent being x to the 4th power with real coefficients. So we don't want any imaginaries in the end. We want all of our numbers to be real numbers. And they give me a 0 of 2, -2, and -7i. So because I have an I here, I know I had to have taken a square root. And whenever I take a square root, I have a plus minus. So technically, I have a plus minus 7i. They've given me 2 solutions, but only wrote down 1 because, again, lazy mathematicians. What else could you expect? And so when I am given my solutions, I know that my solutions typically end up, whenever I'm solving, as x is equal to. So I have x is equal to -2, x is equal to +2, and x is equal to plus minus 7i. In order to have gotten that plus minus, I had to have taken the square root. So in order to undo it, I'm going to square both sides. So I'm going to have x squared is equal to 7 squared is 49, and I squared is -1. So a -49. And in order for these to have been solutions, they had to have been set equal to 0. So I'm going to do that for all of those. And all of these things that are equal to 0 are my factors. And I know factors multiply together in order to get my polynomial. So I'm going to multiply all of these factors together in order to get my final polynomial. Now that I've done all my multiplying and simplified all my like terms, I get my final solution of x to the 4th power, which they told us it should be to begin with, plus 45x squared minus 196. Notice I don't have any more imaginaries. I got rid of them when I did the square at the very beginning, so all of my coefficients are real and I am finished. And it looks like the rest of these I'm saving for my kiddos. I hope you guys really enjoyed this and I hope you learned something. If you did, please like and subscribe. And if you feel like you know someone who could use a little bit of this, it would be helpful for them, please feel free to share. Spread the love.